Welcome back, everyone, and this is Professor Bright. We are going to now look at a new topic, vectors. And so you can see our goals for this section, and we're going to have 5 videos in total for this section. But this first video, we're going to look at just kind of understanding what vectors are first, and then also thinking about some of the geometry related to vectors. And to help us explore what vectors are, we're going to hear from Vector from Despicable Me. Here we go.
Hey, I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
And so Vector kind of summarized what a vector is, but now before we go in and talk about their geometry specifically, he noted that a vector has both magnitude and direction. Well, not all quantities in the real world have magnitude and direction. So, for example, when you're driving a vehicle, you don't have necessarily a vector quantity associated to it. Most commonly, we all pay attention to this, is our speedometer. So that measures our speed that our car is traveling, and that is just a number associated to it. There's not necessarily a direction. When you talk about speed in a certain direction, that is then known as velocity. So similar concepts, just again, do you have a number, which is a magnitude only, or do you have a magnitude and direction? Another example of a scalar quantity would be distance, right? You can say you ran 2 miles, right? But if you talk about distance in a certain direction or an amount of distance in a certain direction, then that becomes displacement. Okay, so be careful when we're talking about numbers. Are they purely just a number? If they are, then that's a magnitude, and then it's a scalar quantity. When we have a number that has magnitude and direction, then that's a vector quantity. Okay, so now onto the geometry. As Vector noted, he said that a vector is an arrow in a certain direction. So, well, here's our arrow, right? We have a starting point and we have the arrow, right, the end part. Mathematically, if you remember from geometry, you might call this a ray, but a ray indicates that it continues forever, and so it doesn't really continue forever. It just goes up until this other endpoint. So really, a vector is going from one point P to another point Q. And so we would give this vector a label, and we would represent it typically by a lowercase English letter with an arrow above it. Okay, let me make that a little bit clearer. So, and the arrow typically indicates the direction. Okay, also this arrow on the line segment here, that indicates direction, but we're actually going to measure direction in a slightly different way. Okay, now this point P that the vector starts at, we call that the initial point. And Q, where it ends, we call that the terminal point. I sometimes use the language of final point, but terminal point is most common. Okay, now Vector said that, a vector has both magnitude and direction. How do we see that from this arrow, right? Well, the length of it, that would be the magnitude. How long is it? Okay, how much of the vector do we have? Okay, and then formally, we talk about direction. If you imagine like a horizontal line here, the direction would be this angle. Okay, you thought you were done with trig. You're not quite, but this would be the direction. Okay, direction we always imagine from kind of the horizontal position and how far we turn counterclockwise from there. Okay, we'll talk about how to measure that more formally in a little bit. Okay, so that's the basic idea of vectors. All right, so if a vector is given by magnitude and direction, how do we do that? And so we're going to kind of discover that through this next example. So we have a vector v, it extends from that to that, and so we have initial and terminal points for both v and w. And then so our question is, are these things equal? Well, I'm going to first visualize this, so let's get a diagram. And I'm going to go 6 in each direction. 2, 5, 6, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. There we go. And so I'm just going to plot these. So -1, 2, 2, 6. Okay, so then this would be vector v. And notice that I'm indicating the direction that we're progressing. So it says from this point, from our initial point to our terminal point. So that's why I have it drawn like that. And w, -5, -1. So it starts there and it ends at -2, +3. So there is w. Okay, and so the question is, are these two vectors equal? Well, what? Oh, and then, okay, I was wondering what it meant to be equal, and it says, okay, so finish reading, Professor Bright. For the vectors to be equal, we need to have the same magnitude and the same direction. Okay, well, so my first question is magnitude. How do I find magnitude? Above, right, we said that the magnitude was kind of the length of the vector. Well, so I need to know how far it is from, so distance from initial to terminal, okay? And now you might scratch your head a little bit here, but really, if we have 2 points, way back in our early algebra days, we learned about the distance formula, right? Distance formula, it tells us the straight line distance between 2 points. And formally, that formula is given by the square root of x, difference in the x's, let me get that notation right, x2 minus x1 squared plus y2, oops, y2, not y squared, y2 minus y1 squared, and then square root of that. Okay, so if I wanted to find, the magnitude of v, and how we represent the magnitude is a double absolute value around the vector. And so I would find the magnitude here. So distance between the x's, so I would do 2 minus a -1 squared plus, and then 6, the y2 minus y1, so 2 squared, okay. So I end up getting, square root of, so 3 squared plus 4 squared, square root of those, and I get 5, okay. And so I do w, do the same thing, and I'm going to say, long story short, you can do the same sort of calculation, and you get 3 squared plus 4 squared is equal to 5. Okay, so magnitude is, to find the magnitude, just do the distance formula. Okay, for direction, now that one, direction, that is going to be given by an angle theta. Okay, so what I want to do is I want to imagine from the initial point, this is very critical, from the initial point, right? Imagine a horizontal line going to the right, and the angle for each one of these is going to be from that horizontal line up to the vector. So again, from W, here's my horizontal line, go from that horizontal line on up to the vector, that's going to be my other angle there. Okay, so now how do I find theta? Well, this is where you might want to imagine a little triangle. Okay, and so I'm going to zoom in here for V at least. Okay, so if I imagine completing this triangle, right, horizontally I would go 3 units, and vertically I would go 4 units. So then I can find theta, right? I can do tangent of theta 1 is 4/3. Okay, opposite over adjacent. Similarly, if I wanted to find theta 2 in this triangle, right, I could draw my triangle. It's a right triangle. Horizontally, I move 3. Vertically, I move 4. So then, again, if I do tangent of theta 2, that's equal to 4/3. Okay, so I could solve for theta, but I mean we have the same equation effectively. So effectively, what I can conclude is that theta 1 is equal to theta 2. So yes, v is equal to w since magnitude and directions are the same. So now we know how to find some basics about vectors, right? We know initial, terminal, we know how to find magnitude, we know how to find direction. Now I want to focus on a little bit more geometry and just say, okay, well, what if we have some vectors geometric, like represented on a grid, and we want to combine them, right? So like I have this example here, and I want to find, say, 2w. Okay, so that means effectively, this 2w, that would be the same as doing w and then adding w to that, okay? And so you might just say, well, isn't it twice as long? And you'd be exactly correct. But again, you have to maintain direction and do twice the magnitude effectively. So direction remains unchanged, magnitude is doubled. So if this is w, right, and w, I just kind of note that we go over 3 units, right? We go to the right 3 and then up 2. So I'm going to make that same motion from where w is. So over 3 and up 2. And so I would add, this would be another w, okay? But now in total, right, if I was looking at the vector 2w, and I'm going to do this in red, 2w would begin where I began with w itself, the first copy of w, and then extend to the very tip of the end of the second one, right? Because a vector goes from initial to terminal. I actually don't care about the journey in between, okay? So 2w would be this vector in red, okay? So that would be my answer geometrically for 2w, okay? Now opposite of v, okay, opposite of v, I am going to look at this. So here's v, right? And if I look at this, this goes to the left 2, and I'm just going to indicate that as negative, and then it goes up, 1, 2, 3, 4, 5, okay? So now for opposite of w, right, when I think about it conceptually, it should go this direction, right? Okay, now that makes sense, okay, but I want to be a little bit more precise. So if I go 2 units to the left and then 5 up, I reverse those for negative v. So if I began here, I could go 2 units to the right, okay, so this would be 2 units to the right, and then down 5. And this is going to overlap with my drawing a little bit. So 2, 4, 5. Something like that. Okay, so this vector in green is going to be negative v. Okay, so that's all fine and well. I'm going to erase this. Undo that. I need to save the vectors. But I want to erase this just so I can see the other information that I have to do yet. So v plus w. Now this one, it sounds like, right, we just need to combine their motion. So we first, if we imagine we start at v, and then we add w to v, really it's just saying from wherever v ends, we have to progress by w. And again, we went 3 units horizontally and 2 units vertically. So from the tip of v, I would say, okay, let's go 3 units to the right and 2 units up. Okay, and so this is what v or w would look like at the end of v. Okay, now what is your actual answer? Okay, your actual answer, which is your resultant vector, okay, that's this definition, it's what you get at the very end, so at the end of combining 2 vectors. So in this case, you would go from the tail, where you begin with v, to the tip of w, okay? So this vector in red would be v plus w. Now, there's another way to do this, okay? You could also place w with the same initial point as v. So I'm going to do that in green. So we would just place, from the initial point of V, we would go 3 units to the right, 2 units up. Okay, great. There's another W. Okay, and then what you can do is to find this same red vector. So you imagine kind of doing the math in reverse. So this math that we did over here, this would be V plus W, but we know that addition is commutative. So what I'm going to do here is actually do W first and then tack on V. Okay, so there's W, and then if I tack on V, right, V goes 2 units to the left. So 1, 2, and then 5 units up. Okay, and so I get the same answer in a different way. Okay, so either way works just fine. Okay, and so we did that one, we did that one, and now V minus W. This one, I prefer to think of this as V plus negative W. Okay, mathematically it's the same. So negative W, right? If this is positive W, negative W would just, slap on negative. So you go 2 units down, 3 units to the left. Okay, so, and again, I'm just going to erase this work so we don't get things confused. Oops, undo. Okay. So I would go 3 units to the left. Okay, so from the tip of V, I would go 3 units left, 1, 2, 3, and 2 down. So this would be negative W. And then again, the resultant would be this vector in red going from the initial point of V, to the tip of W. So V minus W would be there. Okay, and again, if you wanted to do it in reverse, so you would say that V and W, or start at the same point, you would go from this initial point, go 1, 2, 3, and then minus 2 for W. Okay, for negative W. So this is minus W. And then you would tack V on from there, and you get the same thing. Okay, so either way, but just with the negative, make sure to represent it as opposite of W. Okay, so longer video, but it gives you a few different examples and some important tools as we look at our journey through vectors. Again, distance is just given by theta. Use that or find that using tangent, and magnitude, we find that by using the distance formula. And then geometrically, if you scale a vector like these first two, just, multiply its magnitude by whatever that number is. If you're combining or adding or subtracting multiple vectors, for each subsequent vector, you place the initial point of the second vector at the tip of the first, or at the terminal point of the first. And your final vector goes from the initial point of the first vector to terminal point of the very last vector.